So this is the first time we've seen this notation right here. Double integral over capital R. That's the way you would write this. Capital R stands here for, you could say rectangle. Later on, capital R is going to be region, so we don't want to confuse the two. But for this problem, R is going to be a rectangle, so you're taking a double integral over the rectangle R of the function of xy dA. What? Area. So this means with dA is really dy dx, right? It's this right there. And dy dx was the little on the ground, dy times dx. That's a little area, right? So you're saying here you're integrating this function of xy with respect to area. With respect to area. Where area is just those two differentials multiplied. Again, these things that I'm saying right now are going to become very important because we're going to have a lot of different integrals as this chapter progresses and as we get into 13. We're going to be integrating with respect to area, with respect to volume, with respect to arc length, with respect to surface area. Lots of things that we're going to have right here. This little d thing is going to mean a lot of different things as we move on. So it's important that we kind of get it now. Start paying attention to it. All right, so we have this. Now notice the notation here. There's two different equivalent forms here. Look at this. I put or here, or. And what's the difference between these two? The x and y's are switched, the dx and the dy's. So notice on this one, if I were to put a bracket around this, and then here a bracket around this, that part right there that I put in brackets is referred to as the inner integral. The inner integral. It's the one on the inside. So look at this first one. Says, look, you have an integral from c to d of f of xy dy, and then outside of that you have an integral from a to b with respect to x. Now, the x variable is restricted between a and b. The y variable is restricted between c and d. So it's important to get the correct limits of integration attached to the correct variables. And that's why when you switch the order and you do it this way, the a and b are on the inside, the c and d are on the outside. Those are both double integrals over that rectangle.
Are they both the same thing?
I was hoping you would ask that. The question was, are they the same? If you do the order differently, do they give you the same answer?
As long as they're not mixed up like you want to do, because you're basically just taking it from one side with respect to the other, and then you just turn it and it's doing it backwards.
Well, I'm about to answer it. I'm about to answer it. The answer is going to be yes, but with a huge asterisk, okay? If you switch the order of integration, your answer is the same. Like if you do the inner one with respect to x as opposed to y, or do it the other way around, you'll get the same answer so long as your region you're integrating over is a rectangle. And that will stop next class. They'll stop being rectangles. So the order of integration in general does not just switch. You can't just switch it. Over rectangles, yes. But rectangles is the easiest case. Well, when you cut up a rectangle on the ground, right? And this was that rectangle. Here's A, B, C, D. We cut it this way, right? And then this way like that. So I could go and start on this row and take this one, this one, this one, this one, this one, and find the volumes above each one. And then move up, go across, move up, go across, move up, go across. Or I could have started here and went down, and then over one, down, over one, down, over one, down. And that would work with a rectangle. However, if we switch it to something like this, where your domain on the ground looks like that instead, so that's your ground, that's the domain, it's not a rectangle, then you can't even do slices this way. Like if you try and do slices this way, and then slices this way. You can't even just sum across because you're going to have gaps that are missing. And so then summing this way, you have a different, yeah, it's a disaster. So, but it'll turn out to be nice, okay? We don't have to worry about it. It's going to be beautiful, but for now, they do switch, and it's fine. All right, so how do we actually compute these? I mean, that's the question. How do we do it? Well, we've got this if we're going to do this integral right here, that means we're going to have to be integrating a function with respect to y, but that function has both x's and y's in it. So what do we do with the x? We treat the x as a constant. Okay, that's how we do it. And then after we actually do that, then we're going to have to do a separate integral after we're done. Now, if we switch the order and we do the one with respect to x on the inside, okay, then we're going to hold y as being constant on that one. And then after we're done, we'll move to the outer one.
So it's almost like the partial.
It's called partial integration. You're holding one constant and going backwards. All right. Let's just do an example. I think that's probably the best way to get into this. Find the volume under 16 minus x squared minus 2y squared on 0, 2, 0, 2. 16 minus x squared minus y squared. I've got a nice picture here for you. Zero, 2, 0, 2 is all x values between 0 and 2, along with all y values between 0 and 2, and it gives you that little box on the ground, right? I'm taking those, and then I have a surface above this. Here's the surface. That's 16 minus x squared minus 2y squared. There it is, just part of it. And I'm taking just the points in this little region and plugging them in. So if I do that, plug them in, I get just that little top. See those points up there on the surface? Correspond with what the square on the bottom. And now we're looking for the volume underneath that. Boom, everything under there. What is the volume of that solid right there? That's what we want, okay? I'll take the surface out. It's a little more interesting to look at it this way. What's the volume of that? Let's do it. So this is going to be a double integral. What are my limits of integration? 0 to 2. 0, 2, 0, 2. You can't screw this up because they're both 0 to 2, right? So but I want us to think about it a little bit more. I'm going to have the function of x and y in here. I'm about to write it down, and then I can do dy dx. I can do it that way, or I can do it the other way, right? I can do it either way. If you do dy first, then the inner integral, which is the one right here, needs to have your restriction on y. The restriction on y comes from this, so it'd be 0, 2. And then you go outside, and the dx corresponds to this one, so that would be also 0, 2. But if this were 0, 5, 0, 6, then it would be 0, 5, 0, 6. All right, that's what we're doing. We are going to, let's replace our function of x and y with the actual function of x and y, which is 16 minus x squared minus 2y squared dy dx. Now, some instructors like to, at this point, separate out the inner integral and then go do the inner integral and then come back and put the answer in here. Like, take this inner one and go write it down over here and go do it. I prefer to just keep the outer one here. Look, integral 0 to 2, out here, dx, and then everything else I'm about to do is this inner part, which is that right there. Okay? Now, what is the antiderivative of this thing with respect to y. That means you're going to treat all x's like constants. So what is the antiderivative of 16? 16y. Okay? What is the antiderivative of negative x squared? Negative x squared y. Good, because you're treating negative x squared like a constant. So the antiderivative of a constant is that constant times the variable. The variable here was y. Good? What is the antiderivative of negative 2y cubed? Negative 2/3 y cubed. See, now that one you treat the variable like the variable. So now, what do we do when we do definite integrals? We find the antiderivative and then we evaluate, right, at the two endpoints. So we like to put this little evaluation bar here. And here in this case, it's y is 0, right, and y is 2. Normally we would just put 0, 2, right? Normally we would, just 0, 2. But because we're going to have multiple variables now, it's important for us to actually say, what is it that we're actually replacing? Are we replacing the x or the y? Well, we're integrating with respect to y, right? So we're going to be replacing y with 0 and 2. This gets especially important when you have functions of 3 variables, because you've got x, y, and z, and so you've got to really know what's getting replaced and what's not. All right, I'm going to continue. So this equals, I still have this outer integral from 0 to 2. Here's my bracket. And then I'm going to make a lot of room here. Bracket, and then I'm going to put my dx. So I still haven't even messed with the outer integral. Just working with what's in here. When we evaluate, we go the 0 in or the 2 in first. Which one goes in? 2 in first, and then subtract from that what you get when you plug in 0, right? So let's plug in. I like to do 2 sets of parentheses. One that represents what I get when I plug in 2. The other one what I get when I plug in 0, and I'm subtracting. So 2's going in for y. Here we go. 32 minus 2x squared minus 16/3. Right? So 32 minus 2x squared minus 16/3. Double check my work. It's Monday, right? 32, 16. Okay. Now we plug in 0 for y.
0.
It's going to kill everything off. All right, so that's good. So now I've simplified the inside. Let's simplify this inside. This is going to be integral 0 to 2. What's 32 minus 16/3? You get a common denominator there? 80/3? 80/3. So you got 80/3 minus 2x squared dx. Okay? Now you're back in Cal 2 or Cal 1. This is just a basic old integral now. So now we're going to plug in 2 and then plug in 0. So we need the antiderivative though. The antiderivative is what? 80 over 3x minus 2/3 x cubed, and we're integrating 0, 2 here. I'll put x is 0, x is 2, even though we really only have one variable in there. So if you plug in 2, we get 160/3. And then we plug in 2 here, get 8/16/3. And then now minus plug in 0, we get 0. So what's that? 144 thirds? 144 thirds. Which is approximate. Anyone who has a calculator?
48.
What is it?
48.
Oh, 48. It's not approximate. It's exactly. Guess I should have just done the math, huh? 48. That's rare that we get a nice integer answer like that. The volume of that very weird shape that's curved and is 48. 48 what? I don't know. It depends. Units, whatever the units are. Cubic feet, cubic inches, cubic miles. All right, that's how it's done. Hold on. Yeah, all right, this one's more interesting. Find the volume under this really cool function, y sine of x times y, on x is between 1 and 2, and y is between 0 and pi. Let's look at this one first. X is between 1 and 2, y is between 0 and pi. So I've drawn the domain here on the ground. There it is. Okay? Very nice, very nice. And now the surface itself. Oh, wow. Okay, that's a crazy looking surface, right? Some weird sort of sine function, but it's got other stuff going on too. And then if I just plug just the range into this, so just that domain rectangle into it, and then try and find the volume between the surface and the x-axis, or the xy plane, and let me just pull that whole surface out of there and you can see what I'm talking about. What do you notice about this one? I've got stuff above and below. I have positive and negative volume, right? Which is weird. But do you remember on integrals in two-dimensional space, if you took the sine curve, let's say, and you were to go from 0 to 2 pi, and you were to find the area, what would you get? You would get 0, wouldn't you? Because when you do integration, it counts this as positive area, and then this as negative area. And that's just because when you measure the height of the function, right, f of x, when you take that Riemann sum, if your rectangle's up here, that height is positive. If you're down here, it's measuring that height as being negative. So they would offset each other, you get 0. So just keep that in mind. That would give you some positive volume and some negative volume. What would that total be? What would it be? That's what we're asking ourselves here. All right, let's do our double integral. Let's set up. We're going to go, I'm going to do the y first. Let's see. 1 to 2 here, and then I'm going to go 0 to pi here. And we're going to get y sine of xy dy dx. Is that correct setup? Do I have my limits of integration in the right place? What's the outer integral with respect to? X. So that means your outer integral better have the limits on x, which they do, right? And then our inner integral is y, so these are restrictions on y.
Isn't it easier to do the opposite? I mean,
What do you mean?
use x, use the other one as the inside integral.
Ah, that's crazy. Yes. It is. It is. But let's all see that. If we try and integrate this with respect to y right now, that means you're looking at this right here and you're trying to treat x like a constant. Big deal, right? So x is a constant. If this helps, just if you're ever having trouble integrating one of these, just replace x with a constant and then ask yourself, how would you integrate that? Because it's the same process. What would this require? Integration by parts. You'd have to do integration by parts on that. So we could. I mean, we shouldn't be too afraid of integration by parts. However, if we reverse the limits of integration, since this is a rectangle, we can do this, right? So if we look at the other option, now we go from 0 to pi and go 1 to 2 here, still y sine xy, but this time dx dy. When we compare that integration, let's see. We would be looking at trying to find the antiderivative of y sine xy. X is our variable, y is a constant. So again, you can give yourself an example of this. 5 sine of 5x. If you were asked to find the antiderivative of this, you could just ignore this 5, right? And then you would just say the antiderivative of sine of something is negative cosine. But then you'd have to scale out, so it'd be like 1/5, negative 1/5, something like that. Yeah. Then you bring your 5 back in, it would kill that 1/5 off. So the point is, this is much easier to integrate than that one is. So when it comes to integrating over rectangles, you do have some freedom of choice here, and you want to look at it before you do it to make sure you're not making your life miserable by doing harder integration. All right? So let's do this one. I think that one's preferred, don't you? Yes. Okay. Let's see if we can't come up with that integral. I can get this one out of here. All right, so my outer integral I'm not touching. That's going to be integral 0 to pi. I'll put a bracket here to separate my inner from the outer. dy on the outside now. You could pull the y out completely, yes, because it is a constant. And then just integrate sine xy. I'm just going to cover it up. What's the antiderivative of sine of xy with respect to x? Negative, say it again, negative cosine of xy, but you have to have a 1 over y out front or divide by y. So I always like to tell my students do 1 over y on the outside. If I cover up that y, the antiderivative of that is negative 1 over y cosine of xy. But then we have to bring that y back in. So this is times y out here. So what is it at the end of the day? Negative cosine xy. And I'm evaluating from where to where? X equals 1 to x equals 2. You see, again, I'm trying to stress to you that it's important to keep track of your variables because that's where little mistakes can happen. If you're having trouble finding this antiderivative, like just make a little note, come talk to me. We'll find a way to make it make sense. But I can't actually just go through integration again here today. Now, here we plug in 2, and then we plug in 1, and things don't get much better, do they? Okay, so if I plug in 2, what do I get? Negative cosine of 2y, and then minus, now plug in 1, so negative cosine of y dy. Before I integrate, I just don't like the way that this is going to look. I'm going to have negative cosine 2y and then plus cosine y. I'm just going to reverse the order and do this. I just move things around. Yes, you could use some identities and clean that up. I'm just going to integrate that because that's ready to go, isn't it? Like I can integrate each of those with relative ease. So this is just going to be sine y minus 1/2 sine 2y. And we're evaluating from y equals 0 to y equals pi. And I think you're going to be pretty disappointed in the answer. It's going to be 0. Because sine evaluated at any multiple of pi is 0, right? So if I go sine of 0, sine of pi or sine of 2 pi, it's all 0. This is going to give me nothing, right? All for nothing. All for nothing. Which means what? Those volumes canceled. Now there's an interesting question you can ask yourself right now, and that's how would you find the volume of one of those pieces then? Right? I mean, we know that the top piece and the bottom piece have volume, and we know they cancel, right? So do you remember how you would do it in Cal 2 or Cal 1? If I were to go back to that example of the sine function, y equals sine x. Of course, if we went from 0 to 2 pi, you would get 0, right? So if I wanted just the top part, you would do what? You would just go to 0 to pi, right? You would go from 0 to pi, stop there at pi, and you'd say, hey, look, man, whatever that is, that's what the other one is, but it's negative, so they offset each other, right? How could you do that here? Well, let me go back and show you the picture. What did we have to use here? We looked at this picture, we said, okay, look at the domain, right? It starts here at 0 and ends here at what? pi, and we say, hey, just look between 0 and pi. Aren't 0 and pi the x-intercepts of that function? Okay, so go back over here. What would you have to figure out in order to do this? Yeah, so what I would have to do is turn this like this. Look at it from the top, right? And I would have to figure out where the surface hit the xy plane, which is here. And it looks like here. I don't know, that might be a mistake, but what I would need to do is instead of integrating over the entire rectangle, I would need to integrate just on this region right here. And this region right here is not a rectangle, understand? But if you look at it appropriately, is our x still between 1 and 2? Yes? Is our y 0 to pi anymore though? No. Our y values are actually stuck between two functions, right? This curve is a function. Question is, what is it? That's some function. I'll call it f2, and I'll call this one f1. Right? Some function here, and then some function here. That's where we're headed. This is what we're going to do later, okay? But I just wanted you to see it in this problem that that would be how we try and attack it if we just wanted that positive part. So I'm trying to get you to compare that to, this is the easy case, integrating over rectangles. Now this is starting to get more complicated, right? And then what we do is we get more complicated, right? We get like, okay, what if you want to integrate over that region? You know, I mean, so you can start getting weird shapes that you're integrating over. How are we doing? Just a little bit more time. Did the sign-in sheet get around to everyone? Fubini's theorem. Every time I say this one, Fubini, I always think of like a magician walking in. I'm Fubini, the master calculator. This is useful. It pops its head up every once in a while. It can really make your life easier on some problems if you use this as opposed to trying to like grind it out. It says that if f is continuous, so you have a nice well-behaved function on the entire rectangle, we're still on a rectangle, then the double integral over the rectangle with respect to area, which is what we just established is a double integral, is equal to this, right? Which is equal to this, which means that what? Integration doesn't matter. So this is a formal statement of what we just said a little while ago. But it's a theorem. It's been proven. So we saw the value of the order of integration a second ago when we integrated sine xy. We don't want to verify this, do we? Do you? Integrate it both ways, do both of them, see that you get the same answer? Okay. All right. Now we have a very special case. This is very nice. If you ever have a function of two variables, but that function can be split up into two functions of each variable individually, then you are allowed to split up the integral. What? Okay, I'm just going to do an example. All right, look at this one right here. Here's what I'm supposed to do. I'm supposed to go, see, limits on, am I over a rectangle here? This is a rectangle, right? So I'm supposed to go from 0 to pi over 2 for x, and also 0 to pi for 2, pi over 2 for y. I'm supposed to be integrating sine x cosine y, and then this dy dx. I could have gone the other order, right? But that's the order I chose. This theorem says that if you have multiplication in here, and you can separate these two functions, sine x and cosine y, and they both individually only contain a single variable. So like sine of x has nothing to do with y, right? And cosine of y has nothing to do with x, right? If you can split this up, if they are, if you're able to break them into two separate factors, then this turns out to be the integral from 0 to pi over 2 of the sine function with respect to x times the integral from 0 to pi over 2 of the cosine function with respect to y. So it's like almost like cheating. It's not cheating, but you're allowed to split it into two separate integrals and multiply them together. This integral we should be able to do easily. This one should be easy to do. Now, why couldn't we do this on the previous problem? The one I had up here a little while ago was y sine xy. Yeah, you have to be able to split it into two factors. The only way you can split it is right here, right? This right here has just y in it, so that's okay, right? But this one over here has both x and y in it, and so you couldn't split that off.
What if there was no y on the sine?
If there was no y here, then you could have split this into the integral with y, integral sine x. Now, notice it's hard to tell with this example, but see these limits of integration, 0 to pi over 2 here? That would have been coming off of this. And this 0 to pi over 2 would have been coming off the restrictions on x. So if this had gone from 0 to pi, let's say, then you go 0 pi here, but this one would have been 0 to pi over 2 still. All right, some properties of double integrals. Double integrals maintain all the properties that you came to love in Cal 2. All the properties that you had carry over here. If you have two functions being added or subtracted, and you want the double integral, you can split it up into two double integrals and just add and subtract them. If you have a constant, the constant can come out. If you have a surface that is always above another surface, then the double integral of that surface should be bigger than or equal to the other surface. So the volume is saying the volume under F should be bigger than the volume under G if F was always above G. Now, how about finding the volume between two surfaces? So the analogy to this, what's that? Yeah, exactly. In Cal 2, sorry, you found the area under a curve, right? And that was the integral. But then we brought in another function. So here's F. We brought in another function, G. And we still went from A to B. And we said, okay, what's this area? And all you said was, oh, it's just the difference of the two, right? You go integral from A to B of F minus G dx. That's Cal 2. The thing here, you needed to know which function was on top and which one was on bottom, right? Same story here. If you have two surfaces, F and G, the volume between them is just the double integral of F minus G. That's it. And you can split it up using the properties of double integrals into two separate integrals, or you can do it all at one time. Really, it just depends on you. Now, visually, here's what we have. We have a rectangle on the ground. Does this spin? This one doesn't spin. Man. Yeah, it's a picture. Oh, well. A rectangle on the ground. You have a function on the bottom. That's the red one right here is like the surface on the bottom. The black part right here is the surface on the top. And then you're trying to find the volume between them, so you're just subtracting the two. There's the homework for that page, or for that section.